Okay, we're going to extend our discussion of the correlation coefficient to uh, de determining that straight line that we talked about earlier for predicting the output variable as a function of the input variable. And that technique is called regression. When we are finished, here's what you will be able to do. We'll later cover the technique for actually doing this in Excel in a separate lesson. But you remember we talked about home prices, and when we're through, you'll be able to develop an equation that says if you give me the number of square feet, I will tell you how to compute a prediction for the selling price of the house. And not only that, I can give you an upper range and a lower range that describes the predicted range of variation for a house of that amount of square feet. So here are the things that we're going to be able to do and that I just described. The output variable that we're going to be predicting is the selling prices of houses, and this is a histogram of that variable. Here is a scatter diagram showing our output variable, selling price, as a function of our input variable, square feet. Here is the output, or the type of information you can get from the regression function in Excel. And this shows a straight line running through the data that I just showed you that it would derive. And also it will give you the formula for that straight line, which says if you want to predict the price of a house, take $46,556 and add to that $123 times the number of square feet. Okay, here is the output of an Excel regression analysis, and the first number that is being highlighted there is the correlation coefficient. In this particular example, we have only one input variable, so this thing that's called multiple R is exactly the same as the correlation coefficient between the input variable and the output variable, or the output variable and the input variable. But in cases where later we will learn how to do regressions with multiple input variables, the multiple R will be the combined correlation of all of the variables with the output variable. And for the single variable regression model, R squared is simply the square of the correlation coefficient between the input and the output variable, and that tells you the fraction of the variance that is explained by the input variable. When we go to multiple regression, or regression with multiple input variables, R squared will tell us the fraction of the variation that's explained by all of those variables combined. Next we have adjusted R squared. And that's actually what you will always want to use instead of R squared. Here's why. If you have a really small sample of data, it could turn out that, but just by chance, you get a fairly large R squared, but the adjusted R squared takes into account the fact that you had a very small amount of data, maybe only 10 pairs of observations. In this case, we had 362 observations, so the difference between R squared and adjusted R squared is minor, so it really doesn't matter. But if you want to be safe, just always use adjusted R squared, and it's more conservative. And next we have the standard error, and this is akin to our old friend the standard deviation. The standard deviation is the root mean squared error when you're using the average as a prediction. This is the root mean squared error when you're using the regression formula for prediction, or the straight line that we're going to talk about. The next number that I've highlighted here is under the column called coefficients, and it corresponds to the intercept The intercept is the constant term in your prediction formula, and that's the number, the prediction you would get if you were to plug a zero into the formula for zero for square feet. And you might say, well, is that the price of an empty lot? No, it's not really, because none of our data contained any empty lots. In other words, there were no houses that had a square feet of zero. So it's always safer to assume that your model is only good for the range of the input variables that you had in your data set. And so if your smallest house was 1,000 square feet, then you would not want to use the model for any houses that were smaller than that, or, for example, an empty lot. And next is the coefficient for the input variable, square foot living. So that number is about $123, and that basically tells you that the predicted price increases $123 for each additional square foot. And we talk about including labels when we provide input for regression. We'll talk about that later, but it's similar to what we talked about with computing correlation coefficients. Always use the labels, and that way they will show up in your output, so you don't have to go back and try to figure out which variable is which if you're using more than one input variable. So the coefficients allow you to write your formula. In this case, predicted selling price is equal to the intercept plus the coefficient of square foot living times the value of square foot living space. The only thing you have to remember about these coefficients is look at them and see if they make any sense at all. For example, if that 123 was negative, that would say the bigger the house, the less it costs, and you would say there's something crazy going on here. So always remember to look at the story that little equation is telling you and saying, does it make sense? So the two coefficients give us the prediction formula that we're going to use, $46,556 plus $123 times the number of square feet in the house. And then we have the standard error, which allows us to predict how much typical house can vary around that prediction. In other words, if we add 3 standard errors to the prediction, that gives us an upper range, and if we subtract 3 standard deviations, that gives us the lower range. And most predictions, or most actual values, should fall within that range of the prediction. So here's an example of something that you should be able to do. If you have the prediction formula and you're told that the square foot of a house is $2,500, the predicted sales price you should be able to compute, and also the range around which prices, the range of variation around which prices might fall. So you plug 2,500 into the prediction formula, and the predicted price is $354,638, and then you add 3 standard errors to that, and that's the upper range of variation, and subtract 3 standard errors, and that's the lower range. So to interpret this, you would say a house that has a square foot of 2,500 would have a predicted price of $354, but that number could actually range between $182,000 up to $526,000, and other factors would account for that extra range of variation, things such as the condition of the house and the size of the lot and how many bedrooms it has, and other factors. And here is a picture of what we have just derived, showing the regression line, and then above that it shows the upper range of variation, and below that the lower range of variation. And you can notice that there's, out of 362 observations, there's a half a dozen or so that fall outside the predicted range of variation. So that gives us a good feel for the accuracy of our prediction model. We also know that the R squared for this was, I think, 6.66, so that tells us how much of the variation we are explaining are with using square feet. And then these points that fall outside the predicted range of variations are particularly interesting points, actually, and you might want to look at those particular houses and say, why did they sell for so much more? It could be, you know, they had a really nice view, or they were on the waterfront. In this case, none of the houses were on the waterfront, but there might be some other explanation for that, and sometimes those explanations give us additional insights. And also, as always, doing this would allow us to flag outliers that were nothing more than data entry errors. Okay, so this is all for single variable regression. We'll later do a little tutorial with Excel to show you how to get these numbers and these graphs, and then sometime later we'll show you how you can get multiple inputs and develop a regression model with multiple inputs. So that's all for this session.